All right, we're looking at even and odd functions today. So we'll see what they are and how that differs from something with even and odd degrees. So it's something we're going to have to be careful about as we get into these things. Okay, so an even function. An even function is essentially even if, when you substitute in the negative, so f of negative x, it's equal to f of x. So one way to look at it is, just any number, and it would have to apply for all numbers, not just some numbers. F of negative 5 would be equal to f of 5, or f of negative 7 would be equal to f of 7. So it needs to be true for all numbers. And then if that is, well, then that means it's even. And we'll see a little bit more about what that actually means about the shape of the graph. But let's just see what it means to prove if something's even. So first of all, let's look at f of x equal to x squared. So let's just see, just like with an example of a number, let's do negative 2. What is negative 2? Well, negative 2 is just negative 2 squared, which is just going to be 4. But what is f of 2? Well, 2 squared is just 4 as well, so f of negative 2 is equal to f of 2. Okay, so that's the kind of thing we're looking for. So the negative number is the same as the positive number when you plug them into the function. But how do we show this for all x's? Well, in this case, it's just x squared, so how we can do that is just, well, let's substitute in negative x, and we're going to get negative x squared. But what do we know happens anytime you have a negative number to an exponent? Well, we know that if it's an even exponent, the negative in a sense will cancel out, and so you just get x squared. But what is x squared? Well, x squared is just the original function. We're just going to substitute that in and say, well, that is just x squared, that is just f of x. But then what we have just shown is that f of negative x is just equal to f of x. On the left-hand side, I start with f of negative x, substitute that in, and then on the right-hand side, I showed eventually that we could get that equal to the original function. And so it's even. Okay, that's a little bit messy, but that's the idea. And we can do the same thing with b here. So let's just test it out with a number. Let's test out negative 1. And then we could try to, if it seems like it's even, then go ahead and show it algebraically. So if we substitute in negative 1, we're going to get negative 1 to the power of 4 minus 2 to the negative 1 squared plus 3 times negative 1. And if you do that, you get 1 minus 2 minus 3, which is just 1 minus 5 is, I think, negative 4. And do the same thing with h of 1, so the positive, and let's see what we get. So we will get 1 to the 4 minus 2 times 1 squared plus 3 times 1. And in this case, we get 1 minus 2 plus 3. 4 minus 2 is equal to 2. But, well, take a look at that. Negative 4 is definitely not the same as 2. So when we plugged in the one negative number and the corresponding positive, they were not equal. So h of negative 1 does not equal h of 1. So, therefore, not even. Okay, and there we've shown the one function is even. If you want to show it's even, you have to show it for all x. That's why you have to do it algebraically with the x's. If you want to show something's not even, all you have to do is show it for one example. And yes, this point at the bottom here is really crucial. An even function is different than something with even degree. If we take a look at h of x, this has even degree because the largest exponent is even, but is not an even function. So they're two different terms, but definitely very closely sounding. So it's easy to accidentally confuse the two. Okay, so how do we know if something is even? Well, you can always check it algebraically, but one quick way that we can see at least a polynomial is even is if all of the exponents are even. Let's just go back up. So you can see in x squared, well, you only have one exponent, it's even. The function ended up being even. If you check the next one, b, well, the 3x there at the end, x would have an exponent 1, which is not an even number. And the other neat thing is, well, how does it actually relate to the shape of the graph? What we can say is that basically it's getting at symmetry. If your function is even, we say it has line symmetry around or about the y-axis. As in, if you look at the left part of the graph, it is symmetric to the right part of the graph. There is that symmetry across the axis. So over the y-axis, it's the same. And those are a few different examples there. Okay, so what is an odd function? Odd functions are similar in terms of the definition. We again look at, well, what happens if we have a negative? And this time, our function is now going to be, if you plug in a negative value, it's going to be negative the original. So this is the main difference, that negative sign outside the function. So let's just see what that means with this first example. So again, let's just plug in a number. And I'm just going to do -2. F of -2, well, -2 cubed is just, since you have an odd exponent, the negative stays, becomes -8. But if you compare that to f of 2, that'd be 2 cubed, which is equal to, well, 8. And what this shows in this, for this particular number at least, so it doesn't show it in general, is that f of 2, or f of -2, is actually just equal to negative what f of 2 was. So we want to show that now for any number, not just for the number -2 and 2. Okay, so let's show this now for substituting in negative x. So if you substitute in negative x, you'd have negative x cubed. But what happens if you have a negative number 2, an odd exponent? Well, it's the same as just doing negative that x cubed. You can, in a sense, take the negative out. You just know it's negative the answer, essentially. Just like we had with the -2 cubed before. And that's the same as, I'll just write it like this, just so that we can see that this is just f of x, the x cubed part. And you have the negative in front, which means it's negative f of x. So therefore, f of -x equals negative f of x. So it's odd. So again, the key thing, anytime you're checking even, odd, substitute in the negative x, and then see what do you get. Do you get negative the function? Do you get the original function? Or maybe you get neither of them. So that's the idea there. Let's just see what the next one gives us. So again, before we get to proving it algebraically, let's just see what happens when we plug in an actual number. So I'll plug in -1, and then we'll compare it to what happens if you plug in 1. So in this case, we have -1 to the 7th, -1 squared, minus 4. And that's just going to be -1 plus 1 minus 4. The 1's cancel, and you're left with -4. Okay, and let's do the same with +1. So if you have +1, it'll be 1 to the 7th, plus 1 squared, minus 4. But that's actually going to be 2 minus 4, which is -2. So we have a case where the negative number does not equal negative the positive number. So it's not odd. Not only that, it's not even. So it's neither of those. So a function doesn't have to be even or odd. It could just be neither of them. So when do we know if something's odd? Well, in terms of a polynomial, again, we can just look at the exponents. As long as all the exponents are odd, then your polynomial is an odd function. And again, we can kind of see up above, that second example had the x squared in it. That was not an odd exponent. So in the end, that polynomial was not odd. Okay. In terms of its shape, what does that mean in terms of its shape being an odd function? Well, you're going to have some symmetry, but it's a little bit different. It's not straightforward symmetry right across like this, where it's like a mirror image, but instead it's kind of rotating all the way around. Or it's like a double reflection, actually, over both the x and the y-axis. So you can take the portion in the top right, just curl it around, and that is actually identical to the portion in the bottom left once you curl it around. And so we call that point symmetry because you're rotating about the origin. So that's the key thing there. Okay, so that's even and odd. That's essentially the definitions. Now let's just work a little bit more in depth with them just to get a better feel for them. Okay, so let's just identify whether these ones are odd, even, or neither. And with that, the kind of symmetry they have. So the first one, and for all of these functions, essentially all you have to do is take a look at the exponents. So the exponents there are 4 and 2, and you might be wondering, what does a constant do? Well, you can think of a constant, like if you were to have an x on it, x to the 0 is equal to 1. It's like it's not even there, but the 0 there is still, in this case, we can think of it as even though we don't really think of 0 in terms of even and odd really in any cases. But here it helps us just to see that the constant is okay for even. Okay, and since all the other exponents are even, this is even. And what that means in terms of its symmetry, well, that means it has line symmetry across the y-axis. Okay, let's take a look at the next one. If you take a look at all the exponents, you don't need to look at the coefficients. It doesn't really matter what the coefficients are, whether they're even, odd. And remember that x is just a 1, so that's okay. So they're all odd. And so therefore, odd function. So it has point symmetry. So just be careful about those two words, point and line symmetry. And then not only that, it's not just any old point symmetry, but specifically about or around the origin. So that's what we're rotating around. That's what that last part is saying. Okay, let's take a look at this last one. See, x to the 6th, 4x to the cube, so on and so forth. Even is 6, or 6 is even, I should say. 3 is odd. And so since it's a mix of exponents, it's neither. I should spell neither, right? So yeah, it's neither even or odd. And so therefore, no symmetry in terms of line symmetry across the y-axis or point symmetry about the origin. Okay. So definitely try these out on your own first, just as you're going through this video. Try it out. It's on your sheet. And you can use the graph or the actual picture to identify it. And I'll just go through it right now, but feel free to have paused it. Okay, so for the first one, you can see you have a mix of even, odd, or exponents, and the graph itself, there isn't symmetry, so it's neither. The next one, you can see it's symmetric across the y-axis, and if you look at the function itself has only even exponents. 3, no symmetry, as well, mix of even and odd, so it's neither. 4, you can again see, oh, it does look like there is a little bit of symmetry, but that symmetry is not on the y-axis. Not across y-axis. So neither. And if you look at the equation, you can see, well, it's a mix of even and odd. So yeah, you can see there can be other forms of symmetry, but what we really care about and are focusing on is across the y-axis and around the origin. Okay, the next one, again, it looks symmetric across the y-axis in this case, and if you take a look at those exponents, well, they're both even, so we can call this even. And the last one, we have the x there in the equation, which is exponent 1 and 2 even ones, so it's neither. And there we have it. That's a look at just quickly identifying those polynomials as even, odd, or neither. Okay, so let's take a look at some a little bit more complicated examples. So those polynomials, they can be quite straightforward when you have it in standard form. In this case, it's not in standard form, it's in factored form. So we want to see, can we still determine if it's even or odd? And if so, well, in this particular case, what is it? So first of all, let's just figure out the degree. So to determine the degree, add the exponents, since it's in factored form. So that's the key. If it's not in factored form, then again, if it's in standard form, just the biggest exponent. All right, and so the degree in this case, degree equals 10. So if this function were to be even or odd, well, it would have to be even, because you're going to have an x to the 10 somewhere there. So check if it's even. Okay, how are we going to check that? Well, what we're going to do is I'm going to actually call this f of x instead of y. Just substitute negative x. And wherever you see an x, change that to a negative x. Negative x minus 1 to the 4th, negative x plus 1 to the 4th. Okay, and then our goal is to see, is this actually still the same as the original function? And this is where we need to use kind of the ideas of, well, what happens when you have an even or an odd exponent? What happens to the number? Well, in the first case, negative x squared is just going to become, well, just x squared, because a negative number to an even exponent is the same as the positive number. With these parts, these factors, let's call them, that are inside the brackets, this is where we need to be careful. Because negative x minus 1, we can't just look at it like that. We need to actually kind of take out the negative first, call it x plus 1. And same thing with the other one. Take the negative out, call it x minus 1. And now we can look at this as a negative number to that exponent 4, a negative number to that exponent 4, since that negative is now in front of the factor, in front of the brackets. And so because of that, we can now drop that negative because it's to an even exponent. So now this turns into x squared, x plus 1 to the 4th, x minus 1 to the 4th. And well, now let's take a look at the top. At the top, we have x squared, x minus 1 to the 4th, x plus 1 to the 4th. It's just in a different order, but the order does not matter. So this is actually the same as f of x. So therefore, f of negative x equals f of x, so it's even. Okay, so these cases where you're in factor form do take a little bit of extra work, but again, you're keying in on what happens to even and odd exponents to the numbers, especially with negative numbers, what happens to those. And sometimes you might have to do a little bit of factoring, so we factored out a negative to be able to deal with it in these cases. Okay, now let's take a look at a situation where you don't even have a function. Well, let's see. So we have a function, just call it f of x. We don't have an equation, let's say, for the function, and we're told it's even. What we want to do is we want to take a look at g of x and show that it is also even. Okay. So let's just write down our given information. It's maybe not the clearest what we need to do at the start because we don't have an equation to work with, but we have f of x is even. I'm writing that down. More importantly, what does that statement mean? Well, it means if I plug in a negative, that is equal to the positive. So f of negative x is equal to f of x. We also know that g of x is equal to f of x plus 4. Okay. So if I want to show that g of x is also even, anytime we're showing even and odd, we always want to, if we're doing one of these like proofs, these algebraic proofs, since we don't have an equation, we can't check the exponents. We need to just plug in a negative. So g of negative x, what happens with that? Well, what's our equation? Our equation is f of x plus 4, so now it's going to be f of negative x plus 4. Because using function notation, you just replace the x with whatever's inside your brackets. In this case, negative x. And then, well, this, we're going to use the fact, use f of x as even. And if we're using that, well, we can say f of negative x is just the same as f of x plus 4. And well, what that line that I just wrote, well, that is the same as the original g of x. And well, that means I can just rewrite that as g of x. What I've shown is g of negative x is equal to g of x, and that is the goal. So it's even. Okay. So that's the idea. When you have kind of things just strictly in terms of function notation, again, plug in a negative, see what happens. Use the information that you already have. So what if we just change that entire question to everything being odd? So let's do the same approach. So we're just going to make some more space down here. So I'm just going to start with f of x odd. So f of negative x, write down your given information. Odd would tell us that it's equal to negative f of x. And then we have g of x is equal to f of x plus 4. Oh, sorry, I should be careful about those brackets. Like that. So now let's substitute in negative x and see what happens. So g of negative x is the same as f of negative x plus 4. Again, we have an f of negative x. So use f of negative x equals to negative f of x and replace that in this equation here. So we're going to get negative f of x plus 4. But is this actually the same as the above? Well, it's not the same, but is it maybe equal to negative the above? Because really what we're trying to do, if we're trying to show it's odd, is we want to show, is it the same as negative the original equation? So if I factor out a negative to get it to look that way, you get negative f of x minus 4. This is not equal to g of x. So g of negative x is not equal to negative g of x. So it's not even. Or I should say it's not odd. All right, there we have that. So that's an interesting case where the looks very similar to the two different parts, but it works for even and not odd. And that's because that vertical shift, the plus 4, is okay for line symmetry, It maintains that, but does not maintain point symmetry. All right, and that's a look at even and odd functions.